Good morning and afternoon, everybody. I think we've got several time zones represented here, so I don't know exactly who to say what to, but hello, and welcome to this month's IARPIC Atmosphere Community Practice meeting. For those of you who are new, I do see some new names and faces. We do meet on a monthly basis, or try to, and every month we have different speakers or conversations that we hold in connection to a broader overarching topic. For the next 3 meetings, we're going to be focused on something called ICARP. Some of you know about ICARP already. Others don't. If you need another I acronym in your world, there is one. And let me share my screen and start sharing a presentation here to give people just a brief overview and introduction as to what ICARP is. So for those of you who are not familiar with ICARP, ICARP is the International Conference on Arctic Research Planning. It's a decadal process that happens to help the international community get together and talk about what the kind of pressing needs of the Arctic research community are at any given time. The reason we're talking about this now is that the next ICARP, which is ICARP-IV, will be held next year in 2025 in Colorado. And so I want to help engage this community, the U.S. Arctic research community, in this process and ensure that people are aware of it and are spreading the news. So just a little bit of information on ICARP. ICARP is very much a community-wide activity. You see a lot of logos in front of you from groups that are studying Arctic processes and even polar processes. There are a few Antarctic groups as well. All of these groups are officially connected with the ICARP process, with the goals of considering the most urgent knowledge gaps in Arctic research priorities for the next decade, and to explore avenues to address these needs. And I would say that this ICARP has some particular relevance because of the fact that the next International Polar Year will be happening within the next decade. So there's a lot of direction setting that I think can come out of this particular ICARP that will help to influence the Polar Year. As I mentioned, it's very much a community activity. It should include information from early career scientists, Indigenous peoples, and local residents to ensure that we have a variety of viewpoints. And the research effort should provide improved understanding and predictive capabilities of a variety of different Arctic systems. So in general, this is an information development and gathering activity to help push Arctic research forward over the next decade. A little bit of history. There have been 3 previous ICARPs. ICARP-I was held in the US in 1995. ICARP-II was in Denmark in 2005, and ICARP-III was in Japan in 2015. Each of these had reports that came out of them. I encourage you to review those to get more perspective on what sort of information comes out of these ICARP meetings. But they are out there on the web. If you go to the IASC website, you can access all of these. There are multiple different ways to connect with ICARP-IV specifically. There's a whole engagement process that has been initiated. And generally, we're looking to, again, make sure that we're engaging a diverse set of groups and through a diverse set of activities globally, not just in the US, but certainly IARPIC and our activities should play into that. I have formally requested that this series of ICARP-focused atmosphere community practice meetings are included as an official ICARP-IV activity. I haven't heard the decision on that yet. That was just done last week, but I hope that that will be approved. And then the reason for doing such things is that then the outputs from these different activities can be tracked and integrated into the ICARP process. So a few ways that you can get engaged with ICARP. You can participate in an ICARP-IV event, such as this one, or other workshops or discussions. If you have your own activities, you can seek endorsement for those activities as an official ICARP activity. You can help to participate through an ICARP-IV survey, or you can submit relevant resources. So if you have reports, papers, or other types of resources that are relevant for ICARP, you can actually submit those through a collection system that's been set up. And again, all of these are available online through the IASC website. I'll have a link to that at the end of the presentation here. But if you just do a Google search for ICARP-IV, you should land in the right places. Just in terms of the timeline, the ICARP-IV process kicked off a couple of years ago with the development of various committees and groups that are helping to implement all of this. The community input phase is currently ongoing. Phase 2 started last year. It's continuing through events like this and other public engagement activities. 2024 will be very important for defining research priorities, and there are what are known as research priority teams that have been organized that will begin to discuss and kind of boil down what the primary priority should be for ICARP-IV discussions. So that's very much an active process for those who are engaged with the Arctic Science Summit Week meeting, which is taking place this year in Scotland. There will be lots of different sessions focused on these research priority teams and their discussions to help facilitate initial direction setting there. And then, of course, those priorities will be kind of finalized in 2025 during the actual ICARP event in Boulder. And then the year after that, implementation of these activities will take place with the final report and implementation of research directions and priorities. In terms of the research priority teams, there were 7 topic areas that were identified. Some are more or less connected with the atmosphere, but specifically these include the role of the Arctic in the global system, observing, reconstructing, and predicting future climate dynamics and ecosystem responses, understanding vulnerability and resilience of Arctic environments and societies, and supporting sustainable development, scientific cooperation and diplomacy, co-production and Indigenous-led methodologies, preparing present and future generations through education, outreach, communication, capacity building, and networking, and then technology, infrastructure, logistics, and services. All of these, of course, are very important for advancing Arctic research. With the Arctic, or the Atmosphere Collaboration Team, now Community Practice, we decided to focus on 3 of these, which I've highlighted here in yellow, as the focus of meetings. And so today's meeting is focused on topic area 1, the role of the Arctic in the global system. And so this is an overview of the meetings that we're planning to hold as a community practice. Again, today's meeting is focused on that first topic area, and we have 3 speakers who will be introduced shortly, giving presentations that help us to understand how the Arctic and the global system interact. Next month, we're planning to have a meeting on topic area 2. That's on the 26th of February, and we're currently working to bring in speakers for that. And then in early April, which is technically our March meeting, but it was going to conflict with the SSW, so we moved it into early April. We're looking at the topic area 7, which has to do with technology, infrastructure, logistics, and services. So please stay tuned for more information on those meetings. So quickly to summarize, I encourage everybody to consider how your activities might help to contribute to this ICARP-IV process, and if appropriate, to seek endorsement to help make your contribution official and help us to track the outcomes of your various activities and meetings. Certainly, if you have any ICARP-IV relevant resources, make sure to submit those through the website that's been set up. Please continue to connect with any ICARP-IV research priority teams that are aligned with your personal research efforts. Check with your colleagues to see if they might be connected to the teams. Look for events that are hosted by the teams to help provide input into these different topical areas, or participate in the survey that exists to provide your own individual input. And then, of course, consider coming to Boulder next year to join the ICARP-IV in person and contribute there. For more information, I have included this link. I think the presentation should all be made available to everybody who attended. So please visit that website for additional details. Thanks for that. And that's a very quick overview and introduction to what ICARP is all about. And having said all of that, I guess while I'm transitioning here and ending my slideshow, if there are any really quick questions or if people have thoughts, we could quickly field those, but otherwise we'll jump into the presentations. Any questions or comments? All right. If not, as I mentioned, we have 3 presenters today. The first presenter will be Pengfei Zhang, and Pengfei, please go ahead. He's going to be talking about atmospheric rivers and their impact on sea ice, or the connections with sea ice, and maybe just give you a quick 5-second intro to yourself as well, Pengfei and other speakers, so that people know who you are. I think you might be muted if you're talking, Pengfei.
Right.
Yeah, that's better.
Okay. Can you hear me now?
Yes. Yeah, you sound great. Thank you.
Hi. Hello. Good afternoon, everyone. I'm Pengfei Zhang from Penn State University. Now I'm an assistant research professor. Firstly, thanks Dr. Boer for the invitation, and also many thanks to Hazel, Meredith, and Tony for the organization. Today, my topic is about the Arctic atmospheric rivers in the Arctic. This work is in collaboration with scientists from UCLA, Columbia University, and the PNL. Many of you may be familiar with atmospheric rivers, which are narrow, long, synoptic jet of water vapor transport. So usually ARs can account for about up to 90% polar moisture transport in the mid-latitude. So 20 or 30 years ago, it's very rare for ARs can reach the polar regions. However, in recent several studies, they have been found that they have reported that the ARs have been observed in the Arctic and also the Antarctic. So there are several studies found that when AR reaches polar regions, they can produce a strong melting effect on the cryosphere, including the ice sheets melt in Greenland and the West Antarctic, polar events in the Weddell Sea, and the record low of Arctic sea ice in the winter of 2016 to 17. In fact, the concept that the moisture transport can lead to sea ice retreat is not novel. This idea can trace back to some studies, maybe 8 or 9 years ago. Those work from Sukuyang's group, Woods et al., and Guzhen's group. Those work has been followed a lot of work in recent couple of years. However, there are still questions remain unknown. It is to what extent the moisture can explain the rapid decline of the Arctic sea ice. So inspired by the work by Hedge and Taylor and Gudrun's work. So in this study, we are trying to reply this question from the perspective of ARs. So firstly, let's say what's the melting effect of ARs on the Arctic sea ice. So in this study, we firstly analyzed all of the AR events in past 42 years during the November, December, January. We only focus those 3 months that because this period is ice recover season. So and the figure on the left shows a CS concentration anomaly during the AR days. As we can see that the blue line shows the negative anomalies. So it's very clear that the AR can produce a significant CS negative anomaly over the marginal seas. Well, it's also contribute slightly to the CS growth in the Central Arctic. If we show the negative anomalies in the percentage of the climatological value, as shown in the figure on the right, we can see that near the ice edge, there are up to 60% of the CS concentration declined due to when AR approaching the S cover. So that's because the ice cover near the ice edge, they are usually newly formed and thinner fragile. So it's very easy to be melted by strong weather events. Okay, so that's let's see what happened in the past 42 years in the AR changes. So the figure on the left shows a long-term trend in AR frequency in ERA 55 during the November, December, January. The figure shows that there is a significant increasing around the North Barents Coral Sea and the Central Arctic to its north. And this increasing trend is robust among 3 renaissance data. This increasing trend coincides with the local CS area decline. Yeah. Oh, okay. Yeah. The line chart here, it shows the area average in the red sectors. Okay. So my main question in this study is to what extent the melting effect of AR can explain the CS decline. Here we employ a new variable, CS area tendency. It's defined based on the daily change of the CS area in the region of interest. Okay, and then we cumulate this daily tendency during the 3 months from November, December to the end of January. And in this way, this variable actually shows a seasonal ice area recovery, as shown by the black line here. It's clear that there is a positive trend in the black line. That's because in current climate, in winter, the surface air temperature in the Arctic is still below the freezing point. So that requires open water freezing in the early winter. So more sea ice lose in summer, faster sea ice grows during the November, December, January. So that's the physical mean of the black line here. Okay, so this line can be divided into 2 parts. One is CS area tendency during the AR days, as shown by the red line, and another one is the CS area tendency during the no AR days, as shown in the blue line. So the negative values in the red lines denote the melting effect of ARs. And we do find there is a significant trend in the red line. It denotes the melting effect of the ARs is indeed enhanced due to the AR frequency increasing in past 4 decades. So if we exclude the impact of AR effects, as shown by the blue line here, so when there is no AR detect, the CS area recovery in the early winter could be even faster. So that means the frequent AR activities prevent the CS area from growing to the extent allowed by the freezing surface temperature. Okay, so based on the red line here, we can simply estimate that the CS area tendency change corresponding to 1% AR frequency change, and then we project this ratio to the AR frequency trend, and we can get the frequency change induced the CS area change. Finally, we compared this result to the total CS area decline trend in the past 4 decades. At last, we estimated that the enhancement of the AR melting effect can explain 1/3 of the total CS area decline in past 4 decades. So that's also indicated that the total contribution from the atmospheric process should be higher than this value. Okay, the last part is is about the model simulation. So here I'll quickly introduce the results. In the AGCM round, they can capture the AR frequency change, where the coupled round forced by the unspecific forcing cannot reproduce the observed AR change. Well, when we nudge the tropical Pacific variability, the model can capture the AR frequency special pattern again. So that means the internal variability from the tropical Pacific is also important for the observed AR frequency changes in the Arctic. Okay, yeah, that's all. Thank you.
Excellent. Thank you very much, Pengfei. Really
Yeah.
appreciate your presentation.
Mm-hmm.
We don't have a ton of time for questions, but maybe while we're transitioning between speakers, if there are any quick questions for Pengfei or comments, please feel free. You can either type them into the chat or raise your hand. And in the meantime, Jonathon, if you'd be willing to pull up your slides and present them, that would be great. Any questions or comments? Okay, if not, we'll move on to our second presenter for today, who's Jonathon Preece from the University of Georgia. Jonathon, please go ahead.
Yeah, everyone hearing me all right?
Yes, sounds
all right.
good.
Yeah, so thanks again for the opportunity to share some of my research with you. I'm joining you all from Athens, Georgia, where I'm currently working as a postdoctoral teaching and research associate in the Department of Geography at the University of Georgia. Oops. So before I get started, I just want to express how fortunate I've been to work on with my collaborators on the projects that have yielded the results I'm going to share with you. The primary source of funding for this work was an NSF Arctic System Sciences grant with my advisor, Tom Mote, working as co-PI and UGA project lead, Marco Tedesco of Columbia University as the lead PI, and Judah Cohen of Atmospheric Environmental Research as co-PI as well. And this work is closely related to research on Greenland ice sheet melt events that we are working on here at UGA as part of a strategic environmental research and development program grant that Tom Mote is also the UGA project lead for. And then all the individuals pictured to the right there are co-authors on a recent paper in Nature Communications, where we published the findings that I'm about to share, and I'll provide a link to that paper at the end of these slides. So our motivation for this work has been to understand Greenland ice sheet surface mass loss, which, as you can see from the light green time series on the top plot, has rapidly accelerated since the turn of the century. And it has, in fact, superseded dynamic ice loss as the primary source of mass loss from the Greenland ice sheet. And this amplification of meltwater runoff has been spurred by a shift in summer atmospheric circulation over Greenland that has been characterized by more frequent high amplitude, stagnant anticyclonic circulation features, referred to in this case as Greenland blocks, that bring persistent warm extremes by delivering warm, moist air from low latitudes. However, as shown by the bottom figure, particularly the blue and orange time series, this increase in Greenland blocking has not been captured by GCMs, so the observed being shown by the black and green lines there, and the blue and orange lines showing the modeled or projected changes in blocking. So the critical question is, are the models right? In which case, what we've observed is just natural variability, and we'd expect things to sort of taper off and maybe regress a little bit in terms of the rate of Greenland blocking and melt of the ice sheet? Or can this change in circulation be attributed to climate change? Or is it a consequence of climate change, in which case we'd expect this accelerated rate of mass loss to continue? So how might climate change be to blame? Well, some have proposed that the shift in summer circulation might be related to a rapid decline in Northern Hemisphere snow cover. And the time series to the left shows annual and 5-year running means of the Greenland blocking index, which is shown in black there and is just the average of the 500 hectopascal geopotential height over Greenland. And then sinuosity over the North Atlantic, which is shown in orange. And that's just a measure of the waviness of the mid-latitude flow in the region. And that's plotted alongside North American in blue and Eurasian in green snow cover extent as recorded by the Rutgers Global Snow Lab. And as you can see, the increase in high amplitude circulation patterns has coincided with a sharp decline in Northern Hemisphere snow cover extent. So to take a closer statistical look at this potential relationship, we detrended these time series and ran a lagged correlation. And what the figure to the right reveals is a clear signal indicating that high amplitude circulation patterns and blocking over Greenland are more common in July of years with low May North American snow cover extent. So snow cover variability represents a substantial change in the surface thermal forcing of the atmosphere, and that has been shown to impact the large-scale stationary wave pattern. So the decline in North American snow cover may have contributed to the shift in summer circulation over Greenland through this mechanism of impacting the stationary wave pattern. So we then employed the 3D wave activity flux to trace any stationary wave response that may explain the statistical relationship. And the top figure here shows the 40 to 60 degree north eddy geopotential height regressed against May North American snow cover extent. And this reveals an enhanced baroclinic signature in years of low spring snow cover with the westward tilt of the anomalies that favors the upward propagation of Rossby waves. And then the bottom figure shows the 300 hectopascal heights regressed against May North American snow cover extent as the contours, and the associated horizontal wave activity flux as the vectors. And so these vectors indicate an anomalous stationary wave forcing that originates at the surface over eastern Canada and then propagates northeast to enforce a stationary ridge that's centered over Baffin Bay, suggesting the low spring snow cover creates conditions that are favorable to more frequent summer Greenland blocking. So there's clearly this temporal disconnect between what we're seeing in terms of the stationary wave response and the period of low snow cover. So the stationary wave response being in July and the period of low snow cover being in May. So to explore the reason for this delayed atmospheric response, the figure on the left shows anomalies in soil moisture, sensible heat flux, and 2-meter air temperature following low May North American snow cover for each month spanning that delayed atmospheric response, so May through July. And what they show is that low spring snow cover leads to an early drying of the soils over North America by June, which is associated with enhanced sensible heat flux and a warm surface temperature anomaly. And this depleted soil moisture persists into July with a significant warm anomaly that aligns with the region of stationary wave forcing in eastern Canada in July. And so it's this snow hydrological effect that we think sustains the thermal forcing of the stationary wave that we observed in July. So we also wanted to see if this mechanism was represented in Earth system models. So we ran a simple preliminary experiment in CESM2. And in this experiment, the model was run in the atmospheric model intercomparison project configuration, which includes an interactive atmosphere and land surface components, and then with prescribed sea ice and concentrations and sea surface temperatures. And so we ran a control simulation in this configuration for 10 consecutive years and just saved the restart files for May 1st of each year. We then modified those restart files by reducing snow cover over North America to 0 on May 1st of each year and reran 3-month simulations from May 1st through July 31st for each of those 10 control years. And so this approach by taking this approach, we were able to test the impact of snow cover while maintaining those other sources of interannual variability. And we can see that the impact of snow cover reduction in the figure to the right, which shows soil moisture deficits and enhanced sensible heat flux with positive temperature anomalies that build into June and July after reducing that snow cover. And so how did this manifest in the models? Well, the atmospheric response to the model for each month from May through July is shown in the column of figures to the right. And I've also copied over the July atmospheric response from the reanalysis data that I showed earlier on the left there. And the symbology between the maps is a bit different, but if you compare the contours and vectors in the map on the left to the shading and vectors on the maps on the right, you can see that the modeled response in CESM matches what is shown in the reanalysis data remarkably well, with the northeast propagation of stationary wave activity enforcing an anomalous anticyclone centered over Baffin Bay. However, in the model, this atmospheric response occurs 1 month earlier in June as opposed to July in the reanalysis data. So kind of pull everything together here using the summary graphic on the right there. Our results indicate that depleted soil moisture in years of low spring snow cover enhances surface heating over eastern Canada, which then forces a stationary Rossby wave that favors ridging over Greenland, which is known to cause widespread melt of the Greenland ice sheet. And our initial prescribed GCM experiment yielded results that spatially mirror that which is evident in the reanalysis data, which is encouraging, although the timing was off by around a month. And this to me is sort of the clear direction for future work. Additional analysis is definitely needed with more realistically prescribed snow cover anomalies in the air system models to see how more natural seasonal snowpack evolution may impact the timing of the atmospheric response. And we would also like to see how well this response is represented across independent Earth system models as opposed to just in CESM. And as I mentioned earlier, all of this that I've presented is documented in more detail in our recent paper in Nature Communications. So I've included the DOI there for that article at the bottom, or you can access that article, which is published open access using the QR code there on the slide. And that's all I have. Yeah.
Great, thank you very much, Jonathon. I really appreciate
Yep.
your presentation as well. Any comments or questions from the group? Because one comment I have is that, you know, there are, of course, also a lot of studies that attempt to link precipitation in the Western US and snow cover in the Western US to the tropics. It seems one more step removed, but I wonder if you've thought much about how some of those connections might play in bringing essentially a kind of domino effect all the way from the equator up into Greenland and beyond.
Yeah, so I guess in terms of sort of a chain, causal chain, I haven't given much thought to that. There are some papers or one paper in particular that ties the increase in Greenland blocking to tropical sea surface temperature variability. Not necessarily ENSO or any mode of variability that's well established, but they do identify one. And so I think that although I don't have maybe the methods planned out yet, I think that's kind of, it would be interesting to explore ways to kind of isolate and disentangle those different effects using the Earth system models, which is why it was so encouraging to see that the response was picked up in the Earth system models. I think it opens up a lot of possibilities.
Any other comments or questions for Jonathon? Po-Chun, would you be willing to pull your slides up while we're transitioning here? All right, looks like no additional questions. So thank you again, Jonathon. I appreciate it.
Thank you.
All right, our third presenter is Po-Chun Chung from the University of California, Santa Cruz. So Po-Chun, please go ahead.
Okay, thanks for the invitation. My name is Po-Chun. I'm a graduate student from UC Santa Cruz, and yeah, I'm glad to be here to share part of my PhD work about CS loss, water vapor increase, and the interaction with energy transport in driving seasonal polar application. Okay. As we know, the polar application is a robust feature of global warming. It presents a strong seasonality, reaching its maxima during winter and the minima during summer. And some popular framework attribute polar application to isospatial feedback and positive electric feedback. This figure shows the contribution of each feedback to warming in climate models. So okay, so where's my raise of hand? Okay, so yeah, a combined mechanism of alveolar feedback and positive electric feedback have been mentioned to explain pole amplification. But some other process like water vapor feedback, dry and moist energy transport are also important. So some study emphasize the water vapor feedback might play a role in pole amplification by amplifying other positive feedback in the polar region. And these positive polar feedback will decrease the polar dry energy transport. However, it remains unclear how these feedback and transport and manifest and interact seasonally. So here we use the radiative transport hierarchy to idealize GCM coupled to a thermodynamic CS model. So this in this model includes the energy flux at base, top, and through the CIs to simulate the CS activity. So including the ice alveolar feedback and the ice thickness change. So our goal is to investigate the role of CIs and water vapor and the interaction with energy transport across the single cycle in pole amplification. So here are some model setting. We use the ocean aquaplaning with seasonal insolation, and there's no clouds and no Q-flux in our idealized model. And the radiative scheme is RTM, which is widely used in climate model. And by comparing the control and the forcing run, we use 4 times CO2 here. We can get the response to CO2, water vapor, and CS loss. And I call it total response. And then we run the ice log simulation. So in this case, the ice will not change with forcing. So by comparing A and B, we can get a response to CS loss. And we further replace RTM with gray radiation scheme, which exclude the water vapor feedback. So by comparing B and D, we can get a response to water vapor radiative effect. And finally, we also run the ice fraction log simulation. So in this case, we fix the ice fraction, but the ice thickness still can change. So in this way, we can separate response CS loss into response CS thinning and sea ice retreat. Okay, so first I'm going to share some temperature response, and then we'll dive into the mechanism. So here shows the annual mean temperature response. So we can separate total response into response CO2, water vapor radiative effect, and CS loss. And CS loss can be further decomposed into CS retreat and CS thinning. In total response, we can find some classic warming pattern, including tropical warming in the upper troposphere and the polar amplification. The former is from response to water vapor radiative effect, and the polar amplification is from response to CS retreat. And here we move on to the seasonal surface temperature response. The x-axis here is season. Can find that the response to CO2 and water vapor radiative effect present weak seasonality. And the seasonality of total response is from CS loss, including the winter warming from CS retreat and winter warming summer cooling pattern from CS thinning. And this CS thinning pattern is because the latent heat of melting sea ice will suppress the summer warming. And the increasing and the CS thinning will cause the wintertime increasing conductive heat flux and lead to a winter warming here. So this pattern consists with previous study. Okay, so to figure out the physical mechanism, we apply warming contribution method. So generally speaking, the surface temperature anomaly can be attributed to frozen, climate feedback, dry moist, energy transport, and surface energy budget, which is the ocean, since we use aquaplaning here. Okay, so yeah, here shows the seasonal polar warming contribution to each response. So in this plot, the dot above 1-to-1 line means this feedback contribute to wintertime polar warming, and below Z means it contribute to summer polar warming. Okay, and we can find that the CS retreat capture most of the dot of total response. So that includes a strong albedo feedback, ocean turn, and dry energy transport. So the story is the albedo feedback contribute to summer warming, but it is balanced by the ocean heat uptake. And during winter, the ocean releases the heat back to the atmosphere and cause the wintertime polar amplification. And this wintertime polar amplification induce a decrease in dry energy transport. And here we move on to the response to water vapor radiative effect. So can find that there's a water vapor feedback contribute to summer warming, and the moisture transport contribute to winter warming. And here shows the seasonal specific humidity anomaly. So can find that the moistening in the summer hemisphere, of course, it will cause the summertime water vapor feedback. But at the same time, you also increase the meridional moisture gradient in winter hemisphere. And that induce an increase in moisture transport. So that's why we have this moisture transport, the blue diamond here, and contribute to wintertime polar warming. And the water vapor feedback and the increasing moisture transport, they have comparable magnitude. So yeah, they cancel out the seasonality. And so that's why the black dot is close to the 1-to-1 line here. And to further understand the role of remote interaction with polar amplification, we diagnose the seasonal energy transport. So this figure, the upper panel shows the seasonal dry energy transport. So can find that the seasonality is from CS loss. And this pattern is highly related to the temperature response, the seasonal temperature response. So for example, the winter warming here caused the decrease in dry transport, and the summer cooling here caused an increase in dry energy transport. And the lower panel shows the moist energy transport. The seasonality of moist energy transport is from water vapor radiative effect. It presents the stronger transport in winter. And yeah, we have talked about it, that is due to the stronger meridional moisture gradient during winter. Okay, so here's the brief summary. We separate the effect of CO2, water vapor, CS retreat, and CS thinning to prolongation by the hierarchy of IDLS model. And the summarized albedo feedback contribute to winter polar amplification through the ocean heat uptake. And the land entity of melting ice will suppress the summer warming. And the winter CS thinning will cause the wintertime warming through the increasing conductive heat flux. And the summer polar warming, which is contributed by water vapor feedback, but you also induce a wintertime polar moisture transfer, and they cancel out the seasonality. Okay, finally, the change in seasonal dry energy transport seems to be a passive response to seasonal warming pattern. Yeah, and our result highlight the importance of interaction between feedback and energy transport on the seasonal polar amplification, and yeah, hope it will improve our understanding of the mechanism. Yeah, that's it. And thanks for your attention. I'm happy to take any comments. Yeah, thanks.
Great. Thank you very much, Po-Chun. Any questions or comments for Po-Chun? Maybe to try to get a little bit of discussion going here, again, if we bring ourselves back to the primary motivation for this meeting, which is to help inform ICARP-IV. We just heard 3 presentations, different admittedly, but three presentations about how the Arctic is connected to lower latitudes in various ways. And thinking in the context of research priorities for the next 10 years, are there things that stand out as critical for helping to better understand these types of interactions or these different connections between the low latitudes and the higher latitudes? This could be observing systems, this could be modeling systems, it could be many different things. It looks like we have a hand up. So yes, please go ahead.
Hi, I was trying to take notes and do work on the side, but thank you guys for the presentations. That was really informative. One of the things that I thought of was the Greenland polar melting and going into the Atlantic Ocean. Would that change salinity and therefore change ocean circulation? And would that have to be incorporated into any of these models that you have based on? Because deep ocean currents usually are created by very cold, very saline waters. And if all of a sudden all of this non-saline water is flowing into the Arctic, would that throw a wrench into any of the models that you have?
Yeah, thank you very much for that question. Responses? I mean, I'll respond by saying, I think, yes, there's a big influence of having a lot of fresh water put into the ocean. I'm not a ocean modeler, so I can't speak to exactly what is incorporated, but I would imagine that some of these impacts would be already accounted for. Jonathon, since your presentation was a little bit connected to the Greenland melt piece of it, I don't know if you have any initial thoughts, or anyone else in the group, honestly, how long or others, if you have thoughts about how ocean models may be accounting for or not accounting for some of these processes, it'd be great to speak up.
Yeah, I know it's certainly a concern, freshening of the waters around Greenland in terms of its impact on the AMOC. But again, I think I would echo and say that I'm more focused on the atmospheric side of things. So if there are any oceanographers in the group, I would definitely defer to them in terms of how that is currently represented within the climate models.
Thank you, Jonathon. And unfortunately, Wisla Maslowski was here. It looks like he dropped off, but he would have been able to give a pretty detailed response to this question, I think. Other thoughts or other responses? Well, perhaps a good example of how many of the ICARP themes that I introduced earlier are clearly interdisciplinary, and granted, this group is largely an atmosphere-focused group, but we need to continue to talk across disciplines. Jessica, do you have another comment, or is your hand still up from the previous one?
Another comment. My undergraduate degree is wildlife biology, so I think in ecosystems. Are you guys in talks with other ecologists on how this might impact food systems, or is that farther down the road for any of you guys? First we figured this out, and then we figure out how these interactions might impact the seals, the fish, the polar bears, the walrus, the whales. That I'm indigenous from the southwest coast of Alaska. Right now I'm working in Anchorage for Alaska Pacific University, and I'm kind of okay, all this information and modeling, how will this impact my people on the coast? How will it impact their hunting and ability to live where might people want to live?
Yeah, thank you. A really good question. If anyone in the group has specific connections as described or thoughts, again, please feel free to speak up. I mean, I know such research is being conducted. It may not be by the people here on this call, but I know there are many studies that are trying to link these processes. I remember seeing a few different papers related to the influence of precipitation patterns and particularly shifts in the phase of precipitation on caribou. And this was focused on Europe, but I do remember, you know, ice on snow events particularly being very bad for some of the kind of terrestrial animals because of the fact that they lose access to vegetation and water and everything else. But you know, I know that such studies are underway. I don't know if anyone on this call is involved directly with those studies, but again, please feel free to speak up if anyone is.
I know there's been some work that's come out of some of the researchers here at University of Georgia that have looked at how freshwater runoff from the ice sheet also will impact algal blooms in the oceans surrounding Greenland. So I know that they've studied that in the context of carbon cycling, but in terms of how that kind of propagates through the trophic chain, that would be an interesting question and not one that I'm prepared to answer, but I do know that that's being looked at or it has been established as sort of these algal blooms that result from the massive influx of fresh water from the ice sheet.
Yeah, thank you, Jonathan. We have a couple minutes left. Richard, please go ahead.
It just kind of struck me from the talks that some of them focused on, you know, the differences in seasons, but also Jonathan's talked about the transfer from the spring season soil anomalies to summertime Greenland melt. I was wondering, you know, just going back to your question about ICARP, whether there should be a stronger focus on seasonal anomalies, seasonal interactions, and perhaps seasonal predictability.
Yeah, I think that's a very good question. And I think our definition of seasons is changing, of course, in the Arctic in some ways because of the fact that we already have these shifts between kind of the solar season and the ice season, for example, as those things are, the phases between them are shifting a little bit in timing with a thinning ice pack. I think the whole question of seasonality is a very good one to consider in our observing and modeling and understanding needs. I don't have a direct answer, of course, for your question. I think it's a pretty broad one, but I do think that the idea that we have to think perhaps more about seasonality now than we ever have because of the magnitude of the changes is a really good thing to consider for the next decade. Any other thoughts on that topic? All right. We're reaching the end of our meeting, so I'd like to just remind people that our next Atmosphere Community Practice meeting will be February 26th. That is the intent. And again, it will be focused on research topic area 2 from the ICARP-IV RPTs, which is observing, reconstructing, and predicting future climate dynamics and ecosystem responses. So perhaps a bit connected to our current conversation just now. I would say if anyone would like to present at that meeting or has material that they think is relevant for that meeting, please reach out to me or Barry Leffer with information on what you would like to present. Otherwise, if you know of someone who would be a good presenter for that meeting, we're happy to take suggestions. So please feel free to reach out to me or Barry or anyone at the IARPIC Secretariat to make those recommendations, and we'd be happy to consider potential speakers. I hope that many of you will continue to join us in the months ahead. Thanks for being here today, and I hope to see you again very soon. And thanks again to our speakers for their excellent presentations today. So thank you.